Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere. Welcome to another installment of Data Skeptic, Graphs and Networks. Today, a topic you might not think would show up in this season. We're going to talk largely about A/B testing. But it turns out in social networks, it's not straightforward how to do an A/B test. Asaf, had you considered this problem before in your own life?
Yes, I have. I have a friend on Facebook, Dror Goldin, who does A/B testing and mentioned to me the challenges of A/B testing on networks because everything is connected. In the case of A/B testing, we want two separate groups, right? We want the test group and the control group. But if everything is connected, then they might influence each other, and then we don't get the test we wanted. We get our test tainted.
Our guest today was working at LinkedIn and bumping into challenges like this. They're trying to help content creators and do A/B tests in that direction. How could we improve that experience? But of course, content creators have to be consumed by people. And there's a lot of crossover. The people I follow, probably their followers are following similar things and so on. So cutting the graph in half, I guess, would be an unrealistic expectation. The world is connected, as you say. So they come up with this interesting clustering approach in order to do an actual good measurement through A/B testing.
Our guest is focusing on the ego networks, as you said, influencers and their followers.
I picked up a really good term during this interview. It's the stable unit treatment value assumption, or maybe SUTVA, I don't know. But that's the assumption here that's getting falsified. You can't presume that anything's in a vacuum. If you make a change in one spot, it can easily propagate out. So a technique like this can help you conduct much closer to the ideal experiment.
Indeed. And another challenge that will be in the episode, not only everything is connected, but also everything changes. It's a dynamic network. So an interesting subject raised here is the time windows that are used to form decisions in the data. So how long is the window that you need to look at the data to get meaningful results from the A/B test? The challenge of deciding on a time window is an open challenge in network analysis. And I want to give a shout out to a paper stated to, I think, 2016 called TPA, Trending Preferential Attachment. It's a paper by Ossi Mokrin. This paper shows that every network has its own tempo.
Tempo like music, I guess that's why they picked that, yeah?
You can say also rhythm. Some networks change all the time, but some networks are changing, but less quickly. What Ossi did in this paper was to show how long is each hub in the network, how long is its 15 minutes of fame, right? Because in some networks it's 15 minutes of fame, in some networks it's just 1 second, right? If we're looking at a network of, let's say, this IP network, maybe it's a millisecond, but in Wikipedia, it might stay be more stable. So using her algorithm might be an interesting way to look at time windows, applying the time window to the network's tempo.
Well, I have a personal anecdote where I had to do something similar to this project in my career. I was working in a local search space, and we wanted to do some geographic-based A/B testing. But many of our customers would advertise in two areas, like a main city and a city nearby. They had a wider, more regional operating area. So if we did a test and someone overlapped it, there could be spillover effects. In our case, we didn't have quite as dynamic of a system as LinkedIn. You were either a national brand or regional. There wasn't like a half national brand for these US companies. So we were able to treat it like the sparsest cut problem, which astute listeners will know is an NP complete problem. So how did I solve it? Well, actually, we were only dealing with something like 40,000 nodes. So it was okay for our thing to run for a couple hours. And then we got our one answer. And then we're able to do some geographic based testing.
Can you elaborate on the...
Essentially, we split the country into we Swiss cheesed up the whole U.S. country into 4 zones, and we knew that it was pretty self-contained. Few people would overlap into 2 zones. We couldn't eliminate it, but we minimized it. That way, if we did some treatment in zone A, we could compare it to zone B, which didn't get the treatment. So we were able to get a diversity of we balanced our cities in terms of certain properties they wanted, like average income kinds of things. But advertisers were less likely to advertise in both areas, thus experiencing some spillover. There's one term maybe we should throw out there and give people a heads up on because it might get taken for granted, and that's the 1-degree label propagation. Is this a pretty standard technique?
Label propagation is a network algorithm, which is pretty standard, but the 1 degree, I guess, it's a customization that our guest did because he needed it for specific reasons and he needed to make it a short runtime. Label propagation is a fast algorithm, but he probably needed to work even faster. The problem with the label propagation, as I see it, is that you need labels. If you don't have labels, it's a problem. And sometimes you invent labels, which is even more problematic.
Yeah, have to make that design choice. Well, there's some interesting design choices that enable this A/B testing work. So maybe let's jump right into the interview.
I am Dr. Behnaz Moradi-Jamei. I am an assistant professor at James Madison University, Department of Mathematics and Statistics.
And can you share a few details on your focus there?
I am mainly focusing on data science and network data science more especially. So I am teaching data science courses, statistics courses, as well as doing research in the field of network data science with ethical consideration.
And what distinguishes network data science from plain vanilla data science?
So when we talk about networks and network data science, we're not just interested in the data points itself. We're interested in the relationship and modeling the relationship and analyzing them between the data points as well as the data points itself.
You'd mentioned that there are ethical considerations as well. What about network data science requires ethics?
What about network data? It does require ethics in many aspects. For example, one of my recent works with a group of undergrad students at JMU. So in this project, we had a collaboration with undergrad researcher and they developed an ethically minded method for community detection in directed friendship networks. They create an algorithm. We actually create an algorithm, friend bra, that introduces a inclusivity parameter. That parameter really, it's adjustable. It adjusts to balance group inclusion with individual representation, which really demonstrate how algorithmic choices affect social group formation.
Great example, yeah. Can you share some details on how you first got interested in community detection?
Well, when I was doing my PhD, I was interested in network analysis for sure. I think that it's probably maybe coming from my own interest, and I do have a lot of networks of friends around me. Having a community around me was always impactful in my life. So, being exposed to network group and having that personal experience, it kind of pointed me, at the point where, hey, I can do this in this framework.
You've got several publications in this area, but the specific one I want to invite you on to talk about is called Community Formation and Detection on GitHub Collaboration Networks. Could you share some details on the project?
As far as my interest to this project, what really drew our team to this project was the unique opportunity that GitHub presents as the world's largest open source platform. And there has been previous studies that, they looked at smaller projects, typically, testing networks for a few thousand developers. But we wanted to really understand how collaboration really works at scale. So in this project, we analyzed about 1.8 million users and their interaction. So the fascinating thing about GitHub is its transparency. Every pull request, every code review, every contribution is visible. This gives us an unprecedented window to how developers naturally organize themselves into communities. It's like being able to observe thousands of teams forming and evolving in real time. What we were particularly interested in was moving beyond just looking at direct connection between developers. We wanted to understand how these communities actually form and function, not just who works with whom, but how stable, sustainable developer communities emerge from these millions of individual interactions.
And where does the data set about GitHub come from? It's obviously all there on the web, but easier said than done. How do you get your data?
So this part, the data collection, was really my colleagues. Brandon was involved in this part. And as far as the data collection, we wanted to look specifically at open source project, not just any repo in GitHub. So we started by looking only at repos that had, one of the 29 machine detectable license approved by the open source initiative. And these are the official open source license like MIT EPIC, GPL, and the others. So this was really important because it helped us filter out things like personal projects, homework assignments, and repo mirrors. So we wanted to focus on code that was actually meant to be shared and requested by the community. And for the actual data collection, we used Julia package called Ghost to gather GitHub activity. So this part of our work was done by my colleague Brandon. And we looked at non-fork, non-mirrored repos, basically original content from GitHub's creation in 2008 through 2019. And we were tracking like who committed the code, when they did it, and what they added or deleted at the collaboration footprints. So the scale of this was pretty impressive, and we ended up with about 3.2 million distinct contributors and about 7.7 million distinct repos in our initial dataset. But here's how it gets interesting. For our network analysis, we focused on users who actually collaborated with others. So after removing isolated users, those users who only worked on their own repo, we ended up with about like 1.8 million nodes, 177 million edges in our network. And, that's a lot of collaboration. So we considered this network to analyze for our project. And we also wanted to look at the international collaboration patterns. So we worked with the data from GH2N to get local information for users that gave us a second network of about 700,000 developers with verified country code. And about 32 million connections between them. It's smaller than the full network, but still one of the largest analysis of international open source collaboration that has been done.
So if you're going to analyze GitHub as a network, you've got to take those things you described and turn them into nodes and edges. What do those look like in your formalism?
Our network was formed by contributors, and so those are the nodes in our network. And if there is a collaboration between them, we would form an edge. Mainly if both contributors contribute on the same repo, so there is an edge between them.
You'd mentioned the international collaborators. How do you even determine whether they're, one country or another?
So if they have verified country code, we only contributors that they had verified country of origin.
Well, one thing I've noticed on some of my public repositories is I'll occasionally get a surprising pull request from like a bot of some kind telling me like, oh, it's a good time to upgrade this package or something like that in my requirements.txt or my package.json or whatever, often for like a security patch. Does that bot count as like a super contributor?
Yes, but In our analysis, we identified about 3,000 bot accounts, about 1% of the nodes, but they had some of the highest degree centrality ranking. So when we compare the network with and without bot, we had largest community size decreased only slightly from like 60% to 15%. Bots serve important maintenance function, but they don't significantly distort community structure, although we try to take them out when analyzing communities.
So then I know one of the most popular community detection algorithms is the Louvain one. Is that an appropriate use for this sort of analysis?
We explored renewal non-backtrack random walk and Louvain method. Mainly, we equipped Louvain with renewal non-backtrack pre-processing. So our main contribution was really developing a pre-processing algorithm to be fed into Louvain algorithm. So this way, we were aiming to improve community detection accuracy by emphasizing on cyclic structure. Why did we pick Louvain? Because our method incorporates this pre-processing in form of edge weights. And Louvain is one of the common and popular methods and scalable methods that takes weighted graphs in compared to other networks. And in my previous work that I developed a Runbrow renewal non-backtracking random walk, I have a comparison of the common community detection algorithms and the performance of the algorithm. I made a comparison, and coupling with my method, Louvain had the best performance and, outperformed the other method.
Well, I'd love to zoom in on that pre-processing. Could you share some further details about the renewal non-backtracking random walks? In 2023, just 10 vulnerabilities accounted for over half of the incidents responded to by Arctic Wolf Incident Response. Wouldn't you like to know how to take them off the table and make life more difficult for cybercriminals? That's just one of the essential insights you'll find in the Arctic Wolf Lab's 2024 Threats Report, authored by their elite team of security researchers, data scientists, and security development engineers, and backed by the data gained from trillions of weekly observations within thousands of unique environments. This report offers expert analysis into attack types, root causes, top vulnerabilities, TTPs, and more. Discover the attack vectors behind nearly half of all successful cybercrimes, why ransom demands climbed 20% from 2023, and find out why 2024 will be an especially volatile year for cybersecurity. I got my copy. You should get yours by going to arcticwolf.com/dataskeptic. That's arcticwolf.com/dataskeptic. Could you share some further details about the renewal non-backtracking random walks?
Our method and the GitHub network, our method is CS, renewal non-backtracking random walk. The key insight was traditional community detection methods weren't capturing the way developers actually collaborated on GitHub. So we developed what we call a renewal non-backtracking walk approach. Imagine you are exploring a city, but with 3 special rules. First, you can't immediately go back to where you just came from. Second, if you complete a circle back to where you started, you begin a new walk. And third, you keep track of how often you use each street, and mainly the last street that circles back to where you started. This is essentially what non-backtracking random walk does. So in our method, these streets are collaboration between developers, and the circles representing groups of developers who regularly work together. So we assign weight to these collaborations based on 2 factors: how likely they are to be part of these collaboration circles, and how many repos the developers share. So when we combine this with Louvain community detection algorithm, we get a much more realistic picture of how developer communities actually form and function. So the key difference in here is that we're not just looking at direct connections, but a pattern of sustained mutual collaboration.
So would it be correct to say that after your pre-processing step, we have maybe more ideal edge weights, and that's the core difference between a traditional Louvain detection and with the pre-processing going on?
Exactly.
So then if you're going to do some pre-processing, we expect a different result on the back end. What does that look like? I'm sure Louvain detects some number of communities. Do you detect more or less, or what does that look like?
Are you asking about in general with Ronbro, or in synthetic networks, or in GitHub project?
Oh, well, I specifically from the GitHub project, since I already know the answer from the paper, but if you want to speak more broadly to how it'll impact in other types of networks, I think that's fascinating as well.
One thing is that it's not just about the quantity, which in the paper we have a detailed, analysis of what was the size of the communities that Louvain was detected, and Louvain coupled with our method, how was the detection. Other than that, with Runbro, with cyclic structures, or even like other structures, we're trying to make community detection a data-driven approach, not just, a hammer that we would like to, apply this hammer on all of our method. We just don't want to have like a very routine algorithm for all types of data set. We want the algorithm to be suitable for the type of data that we're using. For example, in the GitHub data network and collaboration world, cyclics and cyclic structure are meaningful in forming communities.
I'm picturing like a triangle that's like three collaborators are all linked, or maybe if there's a few more, it's a dense structure there. That's the core idea of a community in some sense, although not necessarily a clique, but finding those cycles, I guess, leads us along that path. Is that a good way to look at it?
Yes, yes. Another practical example would be like considering three developers working on a shared repo. Developer A commits code, B reviews and suggests changes, C integrate these changes and add new features. Developer A then reviews C's work. So this forms a collaboration cycle that our method identifies this as meaningful community structure, unlike simple like star pattern. So the way that Louvain treats this kind of structures is like, it doesn't value this kind of structures, and it doesn't value the importance of this kind of structures. As you know, it's only based on edge frequency. So star-like patterns, where many developers just submit to a central maintainer, these patterns could be the same from the point of view of, Louvain algorithm itself. Louvain algorithm is a valuable method that considers edge frequency, but we want to add to the Louvain, adding other structures and contextual information, coupling with other structure that are context specific would be a really important progress in terms of community detection.
Could you expand on the contextual information? What other features can you append to a user that might be useful?
So just before going on to the team formation and other node attributes, so in this paper, like in this specific work, we weight the edges based on the cyclic structure, which is the probability of participating in cycles, as well as the contextual information, which in here was the number of shared repo between collaborators. So, and we use these weights to enhance, Louvain community detection. But as far as our other interesting findings, we analyzed team formation in OSS networks. This process often follows, preferential attachment, meaning that new members tend to join established communities with well-connected members. And we also found that factors like location and programming language play an interesting role while location showed some influence, primarily coding language was a more significant factor, which leads to stronger collaborations among those using the same language. So really this suggests that shared technical skills are key to team cohesion in open source software projects.
To my knowledge, there's no way on my GitHub profile to specify the languages I know. How do you determine what language a user codes in?
Well, that was really one of the challenges that we were facing. So we tried to assign, one of our analysis was to assign the primary language, programming language to each of the contributor based on the amount of committing by that language.
So then can we talk a little bit about the differences between the communities you detected using the pre-processing method, the runbro on the data to set edge weights, versus what you would get if you hadn't done that pre-processing?
The combination of Ronbro with Louvain led to redefinition of what we call a community in OSS network. So we observed that typical community size falling between 3 to 150 members, aligning with social science finding on cognitive limit of stable group size. And this breaks down large, loosely connected groups, preserving more accurate community structure. And interestingly, we found that language consistency within a community was higher under most assignment role, which shows that contributors naturally cluster with those who work in similar languages, and the impact of location was less clear, which suggests that technical skills and project need rather than geographic proximity derives OSS community formation. So really this was our main finding when we couple Louvain with our pre-processing method. So the combination of, like I said, Louvain and Ronbro was giving us a redefinition, I would say, of communities in OSS, which the traditional community detection methods such as Louvain, they often, cluster thousands of users together. But our approach showed that OSS communities are typically smaller and more closely bonded, often ranging from 3 to 100 members. So we believe that, this smaller community size provide a better understanding of genuine collaboration relationship with OSS, where each member has a better influence and connection with other within their group. We also saw that Runbro and Louvain combination, they helps avoid grouping loosely connected members into oversized communities that lack meaningful interaction. For example, in our result, we had that 95% of the network falls into community size of 3 to 150 members, which contrasts sharply with Louvain alone, where only 30% of the network would fall within this range. So this really suggested that Louvain and Rombro captures the essence of OSS collaboration because it focuses on smaller and more cohesive groups.
So having that more robust structure and with the pre-processing and then Louvain, what sort of insights can you then derive from that more clear picture of OSS contributors?
So I think I can start by the limitation of our work and the limitations that we had and how we can go from there. So one of the limitation of our study was the challenge of assigning a primary programming language to contributors. So as GitHub, as you know, doesn't provide this data directly, at user level. So we had to infer this attribute from contributors' activity across repos, which required some assumptions such as, determining a user's primary language based on the most frequently used language or the language of repo they contribute to most. So this approach may miss finer detail about users who work in multiple languages. And another limitation that our focus on cyclic collaboration may overlook weak but still meaningful connections where contributors don't frequently collaborate but might play essential role in bridging communities. So I think it would be great to refine language assignment further by perhaps using machine learning models to analyze language usage pattern in greater detail. And additionally, I'm interested in exploring other user attributes, such as the contributors' involvement in specific types of projects or their experience level to see if, these factors influence community formation. We could also look into hybrid models that could capture both strong cyclic and weaker bridge connections, which could give us a fuller picture of OSS communities by identifying not just the core groups, but also the individuals who act as, connectors or influencers between groups. So these insights, I think, would be valuable for both researchers and OSS community managers. And hopefully it can offer a more nuanced view of how contributions flow within these global projects.
I think your work is very descriptive of that, showing, how communities develop. But does it necessarily yield any advice for one of those community managers and how they can successfully develop and grow that community, or maybe just define what a successful community looks like?
So, I think this is where I get really excited about the practical implication. For project maintainers, our findings suggest that focusing on building a core team of around 3 to 150 people who can actively collaborate is more sustainable than just trying to get as many as contributors as possible. So for individual developers looking to contribute to open source, it suggests looking for communities where you can engage in genuine collaboration, not just submitting fixes, but actually becoming part of the development cycle. And the language affinity we found suggests focusing on project in language you're already comfortable with might lead to more meaningful contribution. Platforms like GitHub could use these insights too. Imagine if their recommendation system could help guide developers to communities where they're most likely to form these kind of sustained and productive collaborations.
We touched on the bots earlier and how they were sort of a potential challenge, but you had a solution for them. I'm wondering if there were any other challenges you had to tackle. For example, some developers use this concept of a monorepo, where everything goes in one, versus having several sub projects that are all implicitly linked.
So the mono repo situation was particularly interesting because you see some organizations, especially larger ones, use these massive repos that contain all their projects. So Google has this famous monorepo that holds most of their code base, and many other companies follow similar practice. So this creates an interesting analytical challenge because in a monorepo, developers who might never actually work together show up as collaborators in our network just because they're contributed to different parts of the same repo. So it's like saying two people collaborated just because they worked in the same office building, even if they are on different floors and never interacted. Yeah, that's a great challenge. And another challenge was what we call drive-by contributions. These are small, one-time fixes like typo corrections or minor documentation updates. So really these create connections in the networks, but they're not really representative of meaningful collaboration. And we had to think carefully about how to weigh these different type of interactions. So then there is the bot issue, right? Which was more complex than, expected. Some bots are really obvious. They have bot in their name, but others more subtle. And those bots can be super active and sometimes, having the higher degree centrality in the network. So we found that, as I discussed earlier, to about 3,300 bot accounts that were responsible for a significant number of connections. And initially, we weren't sure whether to filter them out or not, but we found that including them didn't significantly distort our community structure. The largest community size, only changed from 16 to 15% when we removed the bots. So we also face challenges with incomplete or inconsistent data. For example, many users don't fill out their location information, but, they put something like, say, planet Earth. So we had to, not consider those. And as far as handling this volume of data was a challenge in itself. So we're talking about 1.8 million developers and 147 million connections. Trying to run community detection algorithm at that scale requires some serious computational resource and careful optimization of the method.
Does that take the form of maybe one really beefy machine, or do you need to go to some sort of distributed approach?
The nice thing about my pre-processing method is that it is highly parallelizable, but you'll need an HPC. A cluster runs in parallel into a cluster, high performance cluster. But each of the runs, it's in the matter of seconds, regardless of the size of the network. So I really need to give credit and say a big thank you to my team at UVA. When I was doing my postdoc at UVA, we did this great work in collaboration with, I was doing my postdoc at UVA School of Data Science, and I was working with a team at UVA Biocomplexity Institute under the supervision of Dr. Gizem Korkmaz, and along with my colleagues, Brandon Kramer and Baywan. So yeah, thank you. And I miss you guys. It's been a while that we haven't been in touch.
Well, the analysis on GitHub is really insightful. Are there any other places you think would benefit from the pre-processing method? Or any other data sets that might be interesting to take it onto?
Yes, I have worked with a group of undergrads, as I spoke earlier, on a project called FriendBro, which we created an innovative algorithm that introduces, first we updated a version of RunBro that was taking the friendship dynamic into consideration, as well as we introduced a inclusivity parameter that we were hoping to do fair community detection using that. So yes, that we have applied this already on the friendship network with a group of great and amazing undergraduate researchers. And our work was published in a IEEE conference. So you can check out my work. It's listed under my Google Scholar webpage. And also, I do think, there is a lot of potential and a lot of fields. So as you know, every network structure has a unique property. For example, friendship network, social network, and every, collaboration network, peer review network, citation network, transportation network. Every network has a unique property, and community has a distinct, I would say, definition in the context of the network. So cycles really might be important in, social networks, but it might not be as important in transportation network. It might be, but there might be other topological structures that are more meaningful depending on the context of the network. So really, I would like to, explore more and develop more unique, tailored algorithms for community detections across, different disciplines. Currently, I have a very enthusiastic student who would like to work with transportation network. We are in a very early phase, so I'm not sure if I'm allowed to discuss any details, but I'm very hopeful of the work that we will do in that project as well.
Yeah, sounds like an exciting opportunity.
Yes, definitely.
Well, I know that's something new and coming up. Is there anything else that you want to highlight that you're currently involved in, or what's next in general?
So what's next in general? I'm really interested in focusing more on network data analytics for social good. I'm really interested in developing, algorithms for community detection or in general for network analysis through an ethic lens. Yeah, that's going to be, I think, my next focus. Although I'm going to be focusing on other machine learning, I would say, aspect of network community detection. I have a project that, I'm exploring network-based neural architect and data-driven methods for community detection in complex structures. But I am having also another project working on state of the art of the community structure validation, developing a hypothesis test for just validating community structure. But I think my main interest right now is focusing on network data analytics and algorithmic development for social good, which is, I'm really excited about it. Yes.
Yeah, I look forward to seeing what comes of that.
Yes. Yeah. Yeah.
And is there anywhere listeners can follow you online?
Yes. Please check out my website, just my first name and last name.com. I am on Twitter and LinkedIn. I will be trying to update my website as frequently as possible. If I have any news, there is a news section. And I'm also trying to have my teaching material publicly available on my website. I'm trying to build a YouTube channel so I could hopefully post my lectures on data science field. I have already started a Python course.
Excellent. We'll have links to all the above in the show notes.
Yes, thank you. Yes.
Well, thank you so much for taking the time to come on and share your work.
Thank you so much for having me here. I was very excited for this podcast, and I'm one of the Data Skeptive podcast listeners. So it's an honor to be here and to participate in one of your interviews. Yeah, thank you for the opportunity.
Oh, it's absolutely my pleasure. Thank you.